Welcome to Math with Professor V. In this video, we're going to answer the question, what is the gradient? And then look at what its applications are. That way you can fully understand what it represents and how you're going to be working with it in your multivariable calculus class. So to sum up, here's the big picture. What is the gradient? It's the generalized derivative of a function of several variables. And what I want you to take the time to do to really convince yourself of this fact is work through and prove that all of our differentiation rules for a function also apply for the gradient. What do I mean by that? I mean, we know the product rule, right? When you take the derivative of a product of two functions, it equals f prime times g plus g prime times f, for example. Well, similarly, if you take the gradient of a product of two functions, yes, that product rule applies. You get the gradient of f times g plus the gradient of g times f, so on and so forth. So it's not very difficult to do. I want you to take the time, prove it to yourself. Also, if you think of some of the applications that you learned for the derivative, for example, when we were finding the linearization for a function of one variable, we knew that L of x was equal to f of a plus f prime of a times x minus a. And similarly, as you should have studied in recent lessons, when we find the linearization for a function of several variables, say just two, you would have f of ab plus, well, we have partial derivatives. Partial derivative with respect to x evaluated at the point times x minus a plus partial derivative with respect to y times y minus b. Well, what does this compose? This composes the gradient. So hopefully you can kind of put some context to the statement, right? That the gradient is the generalized derivative of a function of several variables. Now, strictly speaking, out of context, if you just want to look at how do you compute the gradient, what is it? It is a vector of partial derivatives. So when you're asked to find the gradient for a function of, let's say, three variables, f of x, y, z, the gradient of f is partial derivative of f with respect to x in the first component, partial derivative of f with respect to y in the second component, and partial derivative with respect to z for the third component. Now, if we put some context with the gradient, it can give us a lot of information. One of the applications or uses is that it gives us the direction of the max rate of change of your function. It basically tells us the direction of the steepest increase. Remember, the gradient is a vector, so it gives us direction. Now, when we take its magnitude, it gives us the actual maximum rate of change of some function. And another application that we work with often is finding a normal vector to a surface using the gradient. We'll look at examples applying all of these uses of the gradient momentarily. Also, the gradient is used to compute the directional derivative, which tells you how fast your function is changing if you walk in a chosen path. It's the gradient projected onto that direction, giving the rate of change along that path. So let's review exactly how do we compute the directional derivative of a function. So you have to have some vector, u, that's given, and the function as well. And it's computed by taking the gradient of f, dotting it with u. Now, say for example, your function is just a function of two variables, and u is a vector in two space with components a, b. The way you would compute it is you would take partial with respect to x, partial with respect to y, that's your gradient, and then dot it with u, I'm assuming u is a unit vector, and we get partial with respect to x times a plus partial with respect to y times b. In this sense, you could think of it like some weighted average of the derivative along a certain direction. If your unit vector was in the direction of the x-axis, its components would just be 1, 0, right? Which means a would be 1, b would be 0, and you would be left with solely partial derivative of f with respect to x. That should make sense. If our unit vector was in the direction of the y-axis, its components would be 0, 1, and then we would get partial derivative with respect to y solely, because these would be swapped. This would be 0, this would be 1. And then if it's any mix in between these two extremes, then you have a little bit of partial with respect to x, a little bit of partial with respect to y, and you obtain your directional derivative. Now, I did state earlier that the gradient gives you the direction of the max rate of change of your function. So let's prove that. That way you really believe it in your heart of hearts and you don't forget it. So we know the directional derivative we can compute as the gradient of f dotted with u. And we've studied before that when you have the dot product of two vectors, that's equal to the product of the magnitude of each times cosine of theta. And this theta is the angle between those two vectors whose dot product you're finding. So it's the angle between the gradient of f and u. Okay, well, let's think about each of these quantities. U is a unit vector like we said. And cosine of theta is limited in what values it can attain. Cosine theta is a max when it equals 1, right? That's the largest that quantity can ever be. And that happens when theta is equal to 0. So that's when we maximize the value of the directional derivative. Well, what does it mean if theta is equal to 0? That means the angle between the gradient and u is 0. Therefore, they are parallel, meaning the gradient is in the direction of u, or u is in the direction of the gradient. Okay, cosine theta equals -1 as another extreme. That's when it's a minimum. And that happens when theta is pi. So we get a min value of our directional derivative when they are pointing in opposite directions. So when your vector is in a direction opposite from the gradient. This is also called the max rate of decrease. Okay. And then another option is cosine theta 0, and that happens when theta is pi over 2, good. And then that means basically the function values aren't changing. I go into this in more detail in the introductory video lecture on the gradient and directional derivatives. So I'll link it in the description if you haven't watched it. So now let's look at some examples evaluating the gradient and looking at its applications. First one, we'll start off super straightforward. Find the gradient of the given function, evaluate it at the point P, and then find the rate of change of f at P in the direction of the vector V. Okay, so don't get overwhelmed, just go. First thing they said was find the gradient of the given function. I can do that. The gradient of f, it's a function of two variables. It's going to be partial derivative of f with respect to x in the first component, partial with respect to y, the second component. So here we go. Partial derivative with respect to x of e to the x times sine y is just going to be e to the x times sine y, and then partial with respect to y, now x is constant, so it's e to the x cosine y. Okay, that's done. Now I have to evaluate the gradient at the point P. So here's the point P. So let's tell the people that's what we're doing. Gradient of f at 0 pi over 3 is going to be e to the 0 sine of pi over 3, e to the 0 cosine of pi over 3, and that's just going to give me 1 times rad 3 over 2 and 1 times 1/2. Done. Okay. Lastly, they said find the rate of change of f at P in the direction of the vector V. So they want the directional derivative of f in the direction of V. Now V needs to be a unit vector. Need V to be a unit vector. How do we make a vector a unit vector? We divide by its magnitude. So I take V divided by magnitude of V. Its components are -6 and 8, and I'll divide by magnitude, so that'll be square root of 36 plus 64. So this is -6, 8 divided by 10, which simplifies to -3 over 5 and 4 over 5. Perfect. So now to compute my directional derivative, I'm simply going to take my gradient and dot it with u. So I had computed the gradient at P earlier. There it is. So we have rad 3 over 2, 1/2. And I'm going to dot that with -3/5, 4/5. Perfect. So this is going to be negative 3 rad 3 over 10 plus 4 over 10. And we can clean that up. Let's put 4 first because it's not negative. Minus 3 rad 3 all over 10. Okay, very straightforward application of computing the gradient at a point, and the directional derivative. Now let's look at rates of change. So find the maximum rate of change of f at the given point and the direction in which it occurs. So here's the keywords you need to hone in on. When they actually ask for the maximum rate of change, that means they want the magnitude of the gradient. And then when they ask for the direction in which it occurs, that means they just want the gradient vector. Okay, direction indicates vector. Max rate of change means give the magnitude of the gradient. So in this case, f of, this should say xyz, my bad. F of xyz is x over y plus z. So gradient of f is going to be partial with respect to x, partial with respect to y, partial with respect to z. So partial derivative of f with respect to x means 1 over y plus z is just a constant, so that's all that's going to remain when we take the derivative. Partial with respect to y, now x is a constant, and you can think you have y plus z to the negative first power, right? So using our power rule and chain rule, you bring the exponent down front. I'll have y plus z to the negative second, and then derivative of the inside with respect to y is just going to be 1. So this is negative x over y plus z squared. And then derivative with respect to z now, it will be the same thing, negative x over y plus z squared. Okay, now we need to compute this gradient at the point that was given, 8, 1, 3. So the gradient of f at 8, 1, 3 will be 1 over 1 plus 3, so that's 1/4. Negative 8 over, what's that? Negative 8 over 4 squared. And then same thing, negative 8 over 4 squared. Okay, so this is going to be 1/4, negative 1/2, negative 1/2. So this answers actually the second part of the question. Find the direction in which the max rate of change of f occurs. Now I'm going to go back and answer the first part of the question and give the actual max rate of change. And how do I compute that again? I take the magnitude of the gradient of f at the point 8, 1, 3, and that's going to be square root of 1/16 plus 1/4 plus 1/4. So those are each 4 over 16s plus another 1 over 16. I have rad 9 over 16. Oh, what a cute and lovely answer. 3/4. Boom. Okay. Now that's all fine and dandy, but we want a little bit more application to that, don't we? I mean, max rate of change of what? Let's have this function represent something. So here we go. We have the temperature T in a metal ball is inversely proportional to the distance from the center of the ball, which we take to be at the origin. The temperature at the point 1, 2, 2 is 120 degrees. So first we're asked to find the rate of change of T at 1, 2, 2 in the direction toward the point 2, 1, 3. Okay, well, you might say, Professor V, what in the world? We don't even have a function. I know, but they gave us enough information to make one. Don't you fret. So the temperature T in a metal ball is inversely proportional to the distance from the center of the ball. So T is inversely proportional. That means it's represented by K, some constant of proportionality, over D, where D is distance from the center of the ball. Well, can we figure out how to represent D in terms of our placement on the metal ball, X, Y, Z? Why, of course, D is the distance from some arbitrary point X, Y, Z on the metal ball from the origin. We're just going to use the distance formula. Distance is going to be square root X minus 0 squared plus Y minus 0 squared plus Z minus 0 squared. Oh, so we can say T of XYZ is equal to K over square root of X squared plus Y squared plus Z squared. Perfect. And then how on earth are we going to find K? Well, they gave me this little nugget of info right here that the temperature at 122 is 120 degrees. So that means the temperature evaluated at 122 is going to be 120, which is equal to K over square root of 1 squared plus 2 squared plus 2 squared. That's square root of 9. So K equals 360. Beautiful. Look at us go. So T of XYZ equals, let me write this as 360 times x squared plus y squared plus z squared to the negative 1/2, because I'm getting ready. I know I'm going to need to take the gradient in just a hot second. Okay, so here we go. First part of the problem says, find the rate of change of T in the direction toward the point 213. So what they want is a directional derivative. They want the directional derivative of T at this point toward 213. So we'll take the gradient of T at this point, and then I'm going to dot it. I need a unit vector that has the same direction as the vector that starts at 122 and ends at 213. Okay, no big deal. We got this. First things first, let's compute the gradient. So gradient of T is going to be, now I could go component by component, but maybe you're noticing something. When you take the derivative here, we're going to have to use the chain rule. Please bear with, it's trash day. Hold on. So we're going to have to use the chain rule, and all of the partial derivatives will start off the same. It's just that chain rule will change. For the x component, I'll multiply by 2x, y component 2y, z component 2z. So I can just factor outside the beginning portion. 360 times negative 1/2 times x squared plus y squared plus z squared to the negative 3/2. They all have that in common. Times 2x will be the chain rule for the first component, partial with respect to x, 2y, and 2z. Okay? And then maybe you notice, oh, these 2's cancel with the 1/2. So I'm just going to be left with negative 360 x squared plus y squared plus z squared to the negative 3/2 times x, y, z. Perfect. So I need the gradient of T evaluated at 122. So that'll be negative 360 over 1 squared plus 2 squared plus 2 squared. That's going to give me 9 to the 3/2 times 122. 9 to the 3/2, that's going to be 27. So this will simplify to negative 40 over 3 times 122. Okay, perfect. Now I need to dot this with a unit vector u that's going to be in the same direction as the vector that starts at 122 and ends at 213. So let me call this P, the first point, Q, the second point. So vector PQ has components 1, negative 1, 1. Now make it a unit vector, divide by its magnitude, so that'll be 1 over rad 3. Ooh, I did not want that to happen. Times 1, negative 1, 1. Okay, so we're nearly there. So the directional derivative of T at 122 in the direction of u is going to be our gradient vector at 122 right there, negative 40 over 3, 122, dotted with this vector u. And I highly recommend leaving those constants factored out. It will make finding the dot product so much easier. Because remember, you can just multiply these constants by one another outside. So negative 40 over 3 rad 3, and then take the dot product of the rest. So 1 minus 2 plus 2, which is just 1. So this is negative 40 over 3 rad 3. Voila, there's our answer. Okay, next part states, show that at any point in the ball, the direction of greatest increase in temperature is given by a vector that points towards the origin. Okay, so say we have this ball centered at the origin and you pick some arbitrary point on it, x, y, z. If you create a position vector from the origin to that point, what would its components be? It would be x, y, z, right? Now look at our gradient vector. Our gradient vector right here gradient of t equals negative 360 over x squared plus y squared plus z squared to the 3/2 times xyz. Okay, when I evaluate this at some point, x squared plus y squared plus z squared to the 3/2, that's not going to be negative. That's a positive quantity. So basically what I have is negative 360 divided by some number times xyz. What is the direction of this vector? Well, I know this vector points away from the origin. And this vector here is in the opposite direction because of this minus sign. So the gradient gives us a vector that points toward the origin. So basically you just need to say, yes, xyz is the position vector of the point xyz, and the gradient basically gives us the opposite of that, so it's pointing towards the origin. Good? Hopefully that makes sense. Okay, last example deals with tangent planes and normal lines. So find the equation of the tangent plane and the normal line to the given surface at the specified point. So the surface has the equation x plus y plus z equals e raised to the xyz, and we're at the point 0, 0, 1. So from what we've studied before, hopefully you've watched that intro lecture, if I write the equation of the tangent plane to a surface, I need a vector that's normal to that tangent plane, and that normal vector is equal to the gradient of our surface at whatever point is given. Similarly, I need a direction vector for the normal line, and it is also equal to, yes, the gradient evaluated at that point that's specified. I'll just put equal signs. These are all equals. So we gotta find the gradient. Let me create a function, xyz. Move over whichever terms you want, all on the same side. I'm just gonna move over e to the xyz. Let me compute the gradient now. So partial derivative with respect to x would be 1 minus yz times e to the xyz. Partial with respect to y is 1 minus xz e to the xyz. And partial with respect to z is 1 minus xy times e to the xyz. Okay, to get the normal, I need to evaluate the gradient at the given point 0, 0, 1. So I'll have 1 minus 0, 1 minus 0, and 1 minus 0. So we get the lovely little vector 1, 1, 1. This is what I'm going to use for n for my plane and for the direction vector for my normal line because it's normal to my surface. And the point that was given, don't forget, was 0, 0, 1. So tangent plane, I have a vector normal to that plane and I have a point on the plane. Here we go. I'll take 1 first component times x minus 0 plus 1 second component times y minus 0 plus 1 times z minus 1 is 0. So this simplifies to x plus y plus z is 1. Boom. Then for the normal line, I'll just give the parametric equations. So I'll have x equals 1 times t plus 0. Y equals 1 times t plus 0, and z equals 1 times t plus 1. And there you go, guys. So basically, to wrap up, the gradient is the generalized derivative for functions of several variables. Out of context, it's just the vector of partial derivatives, but we see that with context, it can give us a lot of information. Now, be sure to check the introductory video lecture on this topic if you haven't watched it already. It's linked in the description. And if you need more help with your multivariable calculus class, then head to my Calculus 3 video lectures playlist. I have the entire course recorded, all my lectures on YouTube. If you need help with your other math classes or you want to review, I have video lectures for everything from pre-calc, calc 1, 2, differential equations, and so much more. Don't forget to follow me on Instagram and TikTok. Subscribe and give this video a thumbs up. Share it with a friend or a classmate who might find it helpful, and I will be back with more content sooner than later. Love you all. Bye.